So.
Yeah, I gave this talk before, but I don't think it was. I spoke about it here. So what I want to talk about is a spectral gap in SL2R, which basically is not, say, for random walks in SL2R, which is basically not captured just by standard Firstenberg theory on Lyapunov exponents. So the background for that is actually a spectral gap in the unitary group, which is the following thing. What we consider are finitely generated subgroups of SU2, but which are not necessarily arithmetic. So you take elements G1, Gk in SU2, and I will have to assume they're algebraic for some technical reason I will come back to immediately. And also that, say, the group is a free group or contains a free group, which in this case necessarily is going to imply that if you take this free group generated by G1, Gk, as a subgroup of SU2, it's going to be Zariski dense, which is the same as topologically dense. So that is because we are in SU2, it wouldn't be true. For instance, in SUD, as soon as you have that the group contains a free group, then this countable group is going to be topologically dense. So then what you can define are the averaging operators. Is the averaging operator corresponding to these elements G1, Gk, which gives you an operator from L2 to L2. And well, the norm of this operator is obviously going to be 2k by letting t act on the constant function 1. But then what is interesting is that you have a spectral gap, which means that if you restrict the operator t to the mean zero functions on the group, the norm is actually less than 2k minus gamma, where gamma is some positive number which is depending on G1, Gk, and well is controlled by what we call a paper by Gamber, Jacobson, and Cernak, a non-commutative Diophantine property. I will come back to that later. So what it really means basically is that when you're taking the irreducible representations of the group SU2 on spaces of homogeneous polynomials, on spaces of homogeneous polynomials, well, on each of these spaces there are going to be some spectral gap, of course, because the group is dense. But this gap is uniform over the representations. So this theorem had a number of applications. In particular, solved a problem of Conway and Radin on the mixing of the quark-reversal tiling and other tilings which were introduced by these authors. And it is also of significance in quantum computation, because what it proves, for instance, is that what is called universal gates in fault-tolerant quantum computation are actually what is called efficient, in the sense that you may approximate general elements of SU2 by words written in these elements G1, Gk, which are, so if you want an epsilon approximation, you need words which are going to be at least the logarithm of 1 over epsilon. And well, the standard Solovay-Kitaev algorithm would give you log 1 over epsilon at some power. In fact, what is proven, what follows from this result is that you can get words of length log 1 over epsilon, although it's not always clear how to find these words, but that's another story.
Sorry, can I ask you a quick question about this theorem? What is the spectral gap? What's the value of the spectral gap? Is that
It's just a norm when you restrict to L0 to L20G.
Right, but it's, oh,
Well,
okay.
the top eigenvalue is 2k.
Yeah, the top eigenvalue is
Top
2k.
eigenvalue.
Yeah,
It's 2k, so the
Yeah.
next one
is the next
So
one.
it's
is,
get-
is down by.
So
Right.
the spectral gap is gamma.
Right,
Yeah.
right. So the proof of this theorem
Now, the
uses.
simplest, I could just take two generators if I want to, right?
Yeah, of course. Yeah. In fact, that's an important point. We'll come back to that. So I should say something about this non-commutative Diophantine property. So this is much more than you really need, but in any case, basically this is the only way we know how to get started in some sense. So we have this G, which is generated by G1, Gk, which are free. So you can start looking at words, reduced words of length L, and so this non-commutative property tells you that if you take an element of length L, which is non-trivial, then the distance from that element to 1 is going to be at least a constant A, which is going to depend on G1, Gk to the power minus L. But A doesn't depend on L. So basically, if G1, Gk are algebraic, this is quite easy to verify. I mean, going back to an argument of Gamberg, Jacobson, Cernak, it's quite easy to verify with height considerations. If we don't have algebraic elements, then that is not something which is presumably necessarily true, but it's not because this thing is not true that necessarily the result I stated before is not correct. Well, let me put it like that, just to answer your question to some extent. It's not true. It's not known to be true. For instance, if you would take for G1, Gk generic elements. You take G1, Gk and measure generic elements, it's not known to be true.
You expect it to be, would you say that's?
Well, I would expect maybe in some sense, yes. It's something, I mean, trying to prove this theorem for non-algebraic elements is probably the most important remaining question there, and it's a very difficult one, I believe. So the proof of this result uses several kinds of mathematics. So there is one part which is not conventional in this area, which is belonging to arithmetic combinatorics and uses things like approximate groups, graph theoretic techniques like Balogh and Meredi-Gauss, and then of course also a version of the sum product theorem which is known as a discrete string theorem in the reals, and then of course uses also some representation theory, which in some sense can be viewed as considerations that in some sense can be viewed as continuous analogues of the Frobenius multiplicity theorem that you would have, say, if you would prove a similar theorem in SL2P. So this theorem, we have generalized this theorem in SUD. Same statement, but of course now, assuming that G1, Gk contains a free group, it's not enough to imply that the closure of this group is all of SUD, which is the least you need, because there are subgroups. So what we have to assume is that the group gamma there is topologically dense, and with that statement, with that assumption, you get the same conclusion. And so there, of course, there is an additional difficulty, is that you have other groups there in SUD, and when you're looking at these random walks, basically you have to make sure that you're not stuck too much in one of these smaller subgroups. So there is another difficulty there, which you may call escape from subgroups, which has been handled with, say, appropriate techniques. Basically, you're using random matrix products, Firstenberg theory, but note that, of course, proximality, because SUD is a compact group, is not going to be, you won't have proximality, but what you still can do is get proximality if you're considering appropriate periodic valuation. So in some sense, these are considerations which are very close to what Titz used, for instance, to prove his Titz alternative. And then, well, you have to do some more algebraic work in some sense to deal with this matter of escaping smaller subgroups, which is a difficulty which is not present in the SU2 case. What I should say is that afterwards, in fact with the same kind of technology, this result has been generalized to the full extent of compact simple Lie groups by Yves Benoit and de Saxé. And so, no, what I want to talk about is a group.
So this one still requires your Yavanti.
Yeah, we don't go out of the list of algebraic groups, so that's all we can basically deal. So this remember when I mentioned the issue of escape from groups, again there one uses the fact that you have algebraic generators, so it's all the time. But I mean, in any case, I have no doubt that such a theorem should be true beyond algebraic elements, but we don't know how to do it. So now I want to talk about a non-compact group, which is SL2R, and looking at the standard representation on the projective line, which I will identify with a circle here, where tau j is the usual projective action of G on L2T, and so we are in a non-compact setting, and of course there you get in a non-compact setting, like Peter Sarnak would be saying, things are much easier to get spectral gaps, but somehow the spectral gaps you're getting, say, from the standard hyperbolicity, they are not sufficient for our purpose in some sense, and we really want to have a spectral gap which comes from different reasons. And the reason is going to be that actually SL2R in some sense looks very much like SU2. In fact, they have the same Lie algebra, and so you could hope to get some mileage of this phenomenon in SU2 to prove something in SL2R. And in a way, the non-compact structure of SL2R is more a burden than somehow something which helps in this context. And I think this will be clear in a moment. So remember that we were talking there about this non-commutative de Fontaine property and a set G of generators, which, for instance, can be taken to be a set of two elements in the SU2 case. Now, here we are going to do something else. SL2R is a non-compact group, so in some sense I don't want to suffer too much hyperbolic effects. And what I want to do is start from a set G of elements, G1, Gk, which are actually quite close to the identity. So what I will do is take a large set. So K should be thought of as something large. So G is a large set of K elements in SL2R, which are close to the identity. So G minus 1 is less than 1 over K for G in this set of generators. And moreover, I'm asking for some de Fontaine property. The best I can hope for, well, if I'm looking at words of length L, I'm going to get K at the power L, basically K at the power L elements. So the best I can hope for is some condition of that kind. And yeah, so assuming that we have such a set G, we can again look at the corresponding averaging operator, which is here. Now, obviously, you cannot expect to have a spectral gap, a good spectral gap, for this operator because all the elements are close to the identity. So, for instance, if you would have a function which has, say, basically that has small, if you would look at a given exponential, say ei theta on the circle, and you would look at the action on that on that particular function f, because the g's are very close to identity, you definitely are going to end up with basically the same function, because the rho g is not going to move f very much. Now, what is going on is that you can find some finite dimensional space which is going to depend on the given set G. So let's call that space V, so that you're going to have your spectral gap. In fact, you can, with a factor half here, and even better, but say half is enough for my purpose, if I assume that f, say, is orthogonal to that space V. So this time, instead of asking for f to be say, in the SU2 case, SUD case, in the compact case, it would be just requiring that f is of mean 0. Here we're asking for more. We're asking that f is in fact going to be orthogonal to a sufficiently large finite dimensional space. And with that, you're getting the spectral gap. And actually, the initial motivation for that was a problem in theoretical computer science I will tell you something about. The result then turned out to be also interesting to settle a problem about, I just mentioned your name, I'm not sure it will still come up later on, so, but it was done. I have witnesses. It was also of interest for a problem that was raised by Kajmanovic about Firstenberg measures, and in fact disproves something that people believe to be true. And then eventually this thing with more work turned out to be relevant to prove something more, at least in a certain setting, about the density of states for the Anderson-Bernoulli model in physics. And I want to just review a few of these things.
So could you go back to the main theorem just really quickly? Well, what is E? What is E?
Oh, just the usual, yeah.
Instead of n less than k, if you just ask n sufficiently large subset of integers.
Which set do we take?
Some holes in that.
Let me see. Where here?
Yeah, in the condition absolute value n less than k. Do you really need all n's in an interval, or some positive density or some distribution?
Wait. So the question is whether I need to.
You want to be orthogonal to that. Right?
Orthogonal, or at least have a small projection on that, or something like that.
Yeah, but if you ask instead of all n's, say you have an n squared.
No, but this is a finite number of exponentials, right?
Yeah.
Yeah. So.
Yeah, but you ask the theta, two theta. If you ask a subset, a sufficiently large subset of integers.
Yeah, I understand. I don't know. Well, I assume not, because you see, basically, these g's are very close to 1, so they are like the identity.
Yeah.
So if you have a function which is which has a small derivative, you're not going to move this function very much, right?
Yeah.
So as soon as n is small, as soon as you're looking for f, e, and theta with n small compared with k, you're not going to, if you take the action on that function, you're not going to move it much.
Yeah.
So in other words, this guy acting, so if you take for f, e, and theta with small n, sufficiently small n, this guy is going to be basically f. So you cannot get an, what you need is to displace f in some sense.
But then suppose you would say instead orthogonal to e n squared theta, can you do that?
No, that wouldn't be true.
Won't be true.
Well, if I take E3 theta, for instance, I would have a problem.
Okay.
So yeah, that question in computer science eventually boiled down, I'll mention the question in the next slide, to the existence of monotone expanders, which is something quite counterintuitive in some sense. So monotone expander is a finite family of continuous maps psi from a subinterval of 0, 1 to 0, 1, such that the following holds. If I take any subset A of 0, 1, say of size of measure, so this is just measurable subset, of size bounded by a half, then what I want is that the union of the images of that set A over the psi's in this collection script psi, which is something I called capital Psi of A, has a measure which is significantly larger than the measure of A, with a factor 1 plus C for some C which is independent of A. So these maps Psi, they have to be continuous and also monotone. So if you have such a thing, so such a thing is what is called a monotone expander. And well, first of all, it's not at all obvious that such things exist. For instance, if you're looking at the history of expanding graphs, at least it's pretty elementary to see that if you're taking a random graph of a fixed degree, say at least equal to 3 or so, this is going to have an expander family. This is going to give you expander families. But it turns out that if you try to create such families Psi by random techniques, you don't get the expansion property. You don't get this property. So in some sense, it's kind of a negative indication that such things exist. And there were other indications for that, which will be clear in a moment. Now, still it turns out that you can find such families, and it's actually very simple how to get them once you have the previous theorem, because you just have to observe that these projective actions are monotone. So if you're looking at the projective action of SL2R, and you're taking a family, G, like in the theorem, so elements close to the identity, then you still have to kill that space V, but killing that space V is not a big deal because you can just, this is just a finite dimensional space, you can add some maps, whatever. What it turns out is that it's quite easy to obtain such a monotone expanding family. So this gives the existence of such monotone expanders, and as far as I know, this is the only construction known. Why was this coming up? Well, this is this question from computer science about dimensional expanders. So what is dimensional expansion? You have a field F, and a dimension expander over Fn is a constant number of matrices M1, Mk, n by n matrices over the field F, where you should think K should be independent of n, with a property that if you take any subspace V of Fn of dimension at most half n over 2, and then you're taking the union of the images of V by M1 and Mk, the generated vector space has a dimension which is at least 1 plus c dimension V. So the existence of such objects, dimension expanders, was proven in characteristic 0 by Lubotsky and Zelmanov using property tau of some appropriate simple groups, and then some considerations, say, basically playing with Hilbert-Schmidt norm of matrices and so on. In any case, it's this really characteristic 0 argument does not work in finite fields. On the other hand, there was a paper, a remarkable paper by Dwyer and Spilka, and later developed further by Dwyer and Wigderson, which showed an easy construction, but quite clever, how to build a dimension expander, assuming that you have a monotone expander. So that kind of brought these monotone expanders into the picture. So since we have these monotone expanders, we also get these dimension expanders in arbitrary fields. The argument of Viren-Spilka is completely independent of the characteristic. I say the ground field doesn't play a role there. Now, why was the existence of such monotone expanders questionable? Beyond the fact that, say, random techniques don't produce them, well, actually, there is a notion of a d-push-down graph, which is a graph on an ordered set of vertices. So you put them on a line, such that when ordered along the spine of a book, the edges can be drawn on d pages, and d is a fixed thing there, and in each page, the edges do not touch. So if maybe think instead of having the psi to be monotone, think of them having them anti-monotone, then it's clear that if you have such say an anti-monotone expander, say, you would be able to draw the edges on D pages where D would be the size basically of the family capital Psi you're going to get there. So what you have are D push-down graphs which are actually expanders. In some sense, this was a little bit surprising because after all, since this graph is drawn on D pages, you can say that you would expect this graph to behave more or less like a planar graph. No, planar graphs, they have always O square root of n size separators. So if you have a planar graph on n vertices, we can remove a set of size square root of n so that you can split the complement in two proportional pieces, say proportional to n, with no edges going from one piece to the other. That is what you call a separator, which is of course not possible if you have an expander graph. So for these push-down graphs, you don't have sublinear size separators, which was kind of a surprising thing.
So John, can I ask you in a general way? So this work you did on with the SL2R, which you're talking about still.
Yeah.
So was your motivation for that this, or was your motivation, the Bernoulli?
No, it was this.
It was this.
And the rest came later. The rest came later, yeah. So the first thing that came later is an issue about Firstenberg measures. So we have a probability measure on SL2R which is proximal, which means that there is an element in the support which is hyperbolic. And in general, say we have a random walk proximality means that you have an element which top exponent is going to be so the largest exponent is going to be simple. Just in that case, it just contains a hyperbolic element. And
it means what?
you would have an element with an eigenvalue of absolute value bigger than 1.
We're supported on eigenvalue bigger than
Yeah. So one element.
Okay.
And then strongly reducible, which means that you don't have a finite collection of low dimensional subspaces, which union is invariant under the action of all the elements in the support of nu. So if you have that, then you have this Firstenberg theory. And in particular, what you have is a unique measure mu. So in that case, we are just looking at the standard projective action. So the measure mu is going to live here on P1R, and it is what they call nu stationary, which means that if you have a function f on P1R, the integration with respect to the measure mu is the same as when you compose f with the projective actions tau j. No, there is no Jacobian factor here, right? So you take f composed with tau j, you integrate in mu, and you average over you average the g over the measure nu. The measure nu can be finitely supported, and in fact that is what we're interested in. So there was a conjecture which is basically the following. that if you have a Firstenberg measure which comes from finitely supported probability, symmetric probability measure on SL2R, it can never be absolutely continuous. So it turned out to be false. In particular, if you're taking a family G, like I described in the theorem, you're going to have a Firstenberg measure which is not going to be only absolutely continuous density, but in fact the density d mu over d sigma is also going to be, can also be made arbitrarily smooth. I don't know whether it can be made infinitely smooth, but it can be made arbitrarily smooth.
By the way, maybe I missed the beginning. Tom Wolfe worked on some problem.
Yeah, but he never went beyond hyperpolicity. You will see that in a moment. There is something very basic there. You will see that in a moment. So it should be mentioned that there has been other work using other methods which gave rise to absolutely continuous stationary measures. But these techniques were using essentially the fact that the random walk was non-symmetric. Say for symmetric walks, this technique somehow doesn't work. So now I want to come to the main thing, which is a spectral theory of lattice Schrödinger operators. So let me just say a few things about that. So we have an Hamiltonian, which is a lattice Laplacian on ZD plus a potential lambda V. So this lattice Laplacian is defined the usual way, and then your V is the diagonal part. And what we're going to do is take the V's independently chosen according to some distribution mu. And then the lambda is the coupling. So that is a model for transport in homogeneous media. This discussion is going to be completely one-dimensional, but of course, in fact, these are the more important questions, which are largely unresolved. The setting can be considered on the d-dimensional lattice, and well, the physical properties there are believed to be considerably different, at least. So in one dimension, there is a theorem which tells you that at any disorder lambda, so non-zero disorder, and any realization of V, so possibly.
This is Pasteur.
Yeah, one dimension.
That's Pasteur. Gaussian.
Yeah. Okay. Well, I'll give you the credit. Anyway, yeah. So it's not. Thanks for pointing this out. Independently of what is a distribution of V, you're going to get pure point spectrum exponentially decaying eigenfunctions, and well, in fact, we are going to come back to the density of states later. Say the integrated density of states is going to be Hilbert. So anyway, that phenomenon is called Anderson localization. It's believed to persist in 2 dimensions, while in 3 dimensions one expects absolutely continuous spectrum, at least in the bulk of the spectrum. What remains from this technology of Anderson, Anderson localization techniques developed to establish Anderson localization is that at the edge of the spectrum in higher dimension, you're still going to have a phenomenon there of point spectrum with exponentially decaying eigenfunctions. But say, as a rule, proving continuous spectrum is considerably harder than proving point spectrum. So what I want to discuss is something related, which are 2 things. The first is the density of states. So from now on, everything will be one-dimensional. There is a theorem by Simon and Taylor which is important in this discussion, and it tells you that if we take the measure mu according to which V is distributed to have a Lebesgue density, and not only that, a little bit more, the density should be in L1 alpha for some positive alpha, then this integrated density of states is going to be in fact C infinity. Now, what is significant about the method is that it makes use of the analysis on SL2R. Of course, at that time, this whole technology of getting spectral gaps for thin groups, in some sense, was not available, and so basically the situation was there that instead of having a random walk with a fixed number of elements, you really had the convolution of a measure, say, which already has a positive dimension. Basically, there is a measure coming from the measure mu, induces a measure to the cocyclone SL2R, is already gets you already some distribution on SL2R. Well, like I said, of dimension 1, quite significant. And then you see that if you convolve that a couple of times, you get basically the whole measure on SL2R. Of course, if you have no measure mu, which would be more singular, or in the extreme case, like in Anderson-Bernoulli, would be discretely supported, you cannot expect to recover the measure on SL2R just by a few convolutions. So the things are harder there. In the discrete case, certainly. In the Hölder case, it still can be done, but it requires some work. So the other result is a result by Germina and Klopp, which is some kind of universality statement, if you want, but no for in the Schrödinger operator setting, not for full random matrices. So it's very different from the full random matrices in the sense that the local eigenvalue statistics is Poisson. So in some sense, what I want to do is go beyond these statements in the sense that we are taking measures mu now which are not as regular. What initially was done is to get these same statements assuming simply that the dimension of the measure mu is positive, what they call Hölder potentials. And of course, the most interesting question was what happens with the Bernoulli case. What happens with the Bernoulli case, especially for small lambda. So I should say that actually most of the theory which was built around the Schrödinger operators is not really a physical theory, because if you're looking at these physical models, of course your potential doesn't take a continuous number of values. Say if you're taking impurities, so you're having atoms in a metal, there are only so many types of possibilities for your impurity. So what is all the most of the mathematics was really developed by using single sites, basically probabilistic estimates which are derived from the distribution of a single site. Of course, if that single site only takes 2 values, you cannot expect having much intelligence from a single site. So you really have to look at the collected effect of these sites. Just to give you an example, the theory in one dimension about Anderson localization is true in the Anderson-Bernoulli case also. But for instance, a statement like in higher dimension that you're going to have point spectrum at the edge of the spectrum for the Anderson-Bernoulli model, this is not known. It's known in the continuous case, but it's still not known in the discrete case. Exactly because many of these techniques that were used, they break down. Why does it work in one dimension? It's because you have a method there, which is the transfer matrix technique, which is very one-dimensional, and somehow allows you to make the link with Firstenberg theory and so on, and also treat. Basically, it's treating things beyond the use of a standard vector estimate, which say for say at least the usual Wegener estimate, when you don't have a good distribution for mu, wouldn't give you anything at all. Just to say that there are many problems in the Bernoulli case, certainly in higher dimension, but in one dimension there is still a problem which is interesting and that I have spent quite a bit of time on. The Bernoulli just means that mu, you will see right away, is that the mu is supported on 2 points.
And
Like the potential just take guys plus
Yeah.
or minus one.
So you have a potential that just
okay,
takes
so
two
it's
values.
probabilities.
So let's denote K the density of states. So script n is the integrated density of states. So there are many proofs that no matter what is, so that's for Anderson-Bernoulli, no matter what is lambda, n is going to be Hölder regular with some Hölder exponent. And there are proofs using martingale techniques, and there are also proofs using harmonic analysis and uncertainty principle. And well, what these proofs give you is this Hölder regularity, but does not seem to go, in fact, beyond that. And so basically the conjecture is that if lambda is small, this thing is not only Hölder regular, but you have a density which is bounded and actually becomes arbitrarily smooth when lambda goes to 0. That lambda has to go to 0 was pointed out by Halperin, who observed that for a fixed lambda, you cannot expect Hölder regularity of an order, say, bigger than this quantity. So when lambda is large, you won't have a Hölder regularity which is all the way up to 1. What I managed to prove is when you take lambda close to 0, you can get this Hölder regularity close to 1, but I never managed to go beyond that. And somehow the real problem was to show that it's not only Hölder regular close to 1, but also has Lipschitz, and actually that you can get that thing smooth. Now, intuitively speaking, what is going on is that when you take the lambda small, which is really needed in view of this Halperin result to have any chance, also the Lyapunov exponents, they become small. So in other words, you have less mixing. So on one hand, you go to infinity. If you take your random walk, you go less fast to infinity, but you also have less mixing. And what comes from this new spectral gap is actually a better mixing rate for such small lambda, which allows you to still proceed and get the right contractive inequalities, say spectral gaps you need in order to establish this smoothness. So the result is the following, and I will discuss it in a moment. So we're taking H lambda, the Anderson-Bernoulli Hamiltonian with coupling lambda. So your potential takes plus and minus lambda's values. We restrict the energy away from 0. That is a technical point. So then what we like to prove is that this integrated density of states is going to be smooth. Well, first we like to prove that the density of states is bounded and then maybe also smooth. And so that should be true, like I said, as soon as lambda is sufficiently small. Now we can do that at least in one case, and this is the first example where this could be established. Namely, what we're taking is lambda sufficiently small, and moreover, we are assuming that lambda is an algebraic number with a conjugate which is at least equal to 1, an algebraic number coming, say, from, let's say, a polynomial of degree bounded by constant c, and with coefficients which are bounded by 1 over lambda at the power c, something like that. So you get certainly plenty examples of that. What I want to say is that there is some similarity with the problem of the usual Bernoulli convolutions. So usual Bernoulli convolutions are measures on the real line that you would be getting by taking plus or minus lambda square, plus minus lambda cube, etc. with the plus and the minus at every step independent. So independent plus minus 1 valued variables. And now, well, instead of taking the lambda close to 0, you want to take the lambda close to 1. So the conjecture is that if lambda is sufficiently close to 1, such measures are always absolutely continuous with respect to Lebesgue measure. This problem is still widely open, but over the recent years there has been considerable progress on that. In particular, there are results, well, there are various people involved in that. There is, well, I probably forgot some. There is Hochmann, Schmerkin, Breuillard, Varjou, and so on. For instance, one result would tell you that if lambda is sufficiently close to 1, say if lambda is algebraic and sufficiently close to 1, depending on its Mahler measure, for instance, then the statement is true. These usual Bernoulli, standard Bernoulli convolutions are going to be absolutely continuous. On the other hand, there is still a distinction between what is going on here and what is going with the usual Bernoulli convolutions. For instance, Erdős observed that if lambda is sufficiently close to 1, these results were sharpened later. If you take lambda sufficiently close to 1, random, then the Bernoulli convolution is going to be absolutely continuous. A result of that kind... In measure, yeah. So a result of that kind we don't have here, and in fact it may not be very feasible, because after all there is also the energy sitting there, so the statement has to be true for all energy, so random. Of course you could say we'll fix the energy and we see what happens for a random lambda. Maybe something can be done there, but definitely it's physically not very interesting because you want the statement for all energy. So there is still a distinction. All I want to say is that in the realm of algebraic numbers there are also developments, recent developments for the standard Bernoulli convolutions. In some sense, what we're dealing with here is a non-commutative version of it.
The dimension is 1 in the previous theorem.
What's that?
The dimension is 1 in the theorem that you just said.
Where?
Here it's in 1D? Or?
Yes. Yeah, everything is 1D. Everything I'm going to tell is 1D, and in fact specific for the, specific for the lattice Laplacian. Because what I'm using is the usual transfer matrix.
You have to be using a lattice Laplacian, but the normalization is also important, right? I mean, because otherwise you can just scale.
In what sense?
Well, because density of states I can multiply the Laplacian potential by any constant. So the coefficients of your Laplacian, you have to have that 1 minus 1 there, right?
Yeah, absolutely.
Yeah.
No, you could rescale, but then you change. No. This transfer matrix formalism basically makes the link with the theory of random walks, and particular Firstenberg theory, which is going to tell you, for instance, that the Lyapunov exponent is going to be positive. And well, we are studying really the integrated density of states, but it's basically the same as studying the Lyapunov exponent, because they are related by Thal's formula, which tells you that one is the Hilbert transform of the other, so proving smoothness of one or the other are equivalent things. So essentially what we like to do is use somehow this new spectral gap result for SL2R in the context of this random walk, except that now we have a random walk not with a large set G of elements which are close to the identity, but we only have 2 elements basically, because we can take V to be +1 and -1. So the way this works is the following. So we have 2 elements, G and G-. They are not close to the identity, but they can be gotten close to the identity with the usual Plücher transformation. And so, in any case, let's look at H1, H2, obtained the way it is written there, which gets you parabolic elements close to the identity. What it turns out, so there are only 2 elements there. Nevertheless, what it turns out is that we have a result which is similar, kind of similar, to the spectral gap result I mentioned earlier. So although we only have these 2 elements, H1 and H2, what we can prove is a spectral gap here. Well, maybe I shouldn't call it a spectral gap. It's basically, well, it's basically equivalent with the spectral gap. What it tells you that if you take any function f orthogonal to an appropriate finite dimensional vector space V, then either the projective action rho h1 or the projective action rho h2 is going to move f away by an amount with the factor lambda at the power 2. Now, that kind of phenomenon is completely standard from hyperbolicity, except that here instead of the lambda at the power 2, you would get lambda. And somehow what I need here is an exponent which is smaller. So in fact, when lambda goes to 0, I can make 2 arbitrarily small. But the truth is that for my whole story, all I need is to get 2 less than a half, for instance. That would already be enough. So basically, the question is, how do you deduce such a statement from the original spectral gap result I mentioned you? Well, you see, you have these two elements, H1 and H2, which are two parabolic elements. And so there is a result, there are several results like that, I will not discuss them in detail. In fact, the simplest result is a result by Sanov and Brenner, which tells you that if mu is bigger than 2, or at least equal to 2, and you look at the group generated by these two elements here, A and B, this group is going to be free. Apparently, this the source, the origin of this research came from Hasse, who was concerned. Hecke, is Hecke concerned with it in connection with what cyclotomic zeta functions or something like that? That's I think Sarah told me it was Hasse. That there is a paper by Hasse who was Sarah. Anyway. So, well, the point is that my mu is not large, it's small. But fortunately, it has a conjugate, which is large. So if the group, if I replace it by its conjugate and you have something which is free, then the original thing is still going to be free. But I still don't have a large set. So what you do is that you just look at the set of elements h1 at the power L, h2 at the power L, L from 1 to k. That gets me where you take the k, say lambda minus 2. So that would give me a set of k elements in the group. And notice something which is important is that you shouldn't consider that as really as words of length of length 2L, because the point is that when you look at these elements, because you have parabolic elements, in terms of lambda, these are quadratic polynomials. This is quite important. And therefore, you can verify, again by height considerations, that in fact, for this family G, you're going to satisfy this Diophantine condition that you need in the statement. So what I'm referring to is the statement which is here. So I wouldn't want to have here, and the L is a different L here. I wouldn't want to have L times K there. But because the thing, elements of G are quadratic in lambda, you're not going to get that. You're going to get that. So what you obtain by looking at these elements H1L, H2L is a family G to which the spectral gap result applies. So you're getting your spectral gap here. In particular, you're getting that f minus rho g, f is going to be bigger than a half for all, say you take the maximum for g in G, for all f orthogonal to an appropriate finite dimensional space. And that implies, because of the definition of the elements in script G, that you're going to have a displacement by the individual elements h1 or h2, which is at least 1 divided by k, and k is lambda minus 2. So you get there something which is much better than what you get from the usual hyperbolicity, which would only give you something like a lambda. So here you can get something which is much larger, and this is a phenomenon that does not come from hyperbolicity. It really comes from the basically the structure of the group of SL2R, which locally is very much like that of the unitary group of a compact group. So what you do then is that you start running the usual machine. So first of all, an observation. What I have here is a projective representation rho with a Jacobian factor. But because my elements are close, at least after the Plugger transformation, are close to the identity by a factor 1 plus lambda, by a lambda or so, and that the spectral gap is much, much bigger than lambda, I can get rid of these Jacobian factors, and I have actually the same statement where the rho is replaced by the tau. So now I'm looking at this averaging operator, which is closer to what is involved in Firstenberg theory, where you compose with the Möbius transformation without the Jacobian factor, and using this basic inequality, which was on the previous, which is written here, but now written with tau. What you can prove are certain contractive phenomena, which translate in very strong smoothing properties. So in particular, what I have here is that the TMF for large M in HS is controlled by the L2 norm up to a factor which is exponentially small, and similar, the L2 norm of TMF is controlled by the H minus S norm of F up to factors which are extremely small. That already would imply right away that Firstenberg measures have smooth density. Why? Well, the first step is to prove that the density is in L2, for instance. So what you do, you have your Firstenberg measure mu, and you hit it with a function which is in L2. But you know that the Firstenberg measure is stationary. So mu f is the same as mu TMF. Okay, now what I have to do is bound mu is bound mu TMF. Now, what you know about the mu from Firstenberg theory, you don't know that mu is absolutely continuous, or certainly that it has an L2 density, but you know certainly that, say, to talk as a harmonic analyst, d mu, d sigma is going to be in some H minus S space, at least for some S. So then you bound the thing, TMF d mu, you bound it by the HS norm of TMF. But the TMF in HS is basically controlled by the L2 norm of F, which was assumed to be bounded. So that already proves that the density of the Firstenberg measure is an L2 is going to be an L2 function, and then using the other inequality, what you can get is that actually it is in HS. So that already gives you the smoothness of these Firstenberg measures. This is why I didn't want to get in further details for this Kajmanovic-Leprin's question and example, because that already gives you right away such an example, and in fact here it's even more striking because you have a random walk on two elements. Now, what we want is the density of states, and so this T satisfies certain large deviation estimates. Basically, if you iterate T enough times, you let it act on F, what you're going to have there in the limit is the average of F for your Firstenberg measure on projective space, and this in fact goes exponentially fast. That is standard theory, and it allows you to prove this inequality which is here. Why is this inequality true? Well, you see, instead of writing TLF, you could write it as, say, let's write T2LF. You can write it as TL of TL f minus integral f d mu plus integral f d mu. Now, since we are looking at a derivative, this thing can be forgotten. So what I'm looking at really is the HS+1 norm of TL, TLF minus integral f d mu. Now, if you go back to the previous transference, I can estimate the HS norm of TL of this quantity. Basically, so I'm using this inequality here. I can estimate it by the L2 norm of f, f being this thing here, which is bounded, which is exponentially small in L by, in terms of the L2 norm of f, from the large deviation theorem, which is here, and then another term, which is the second term here, which gets me exponent minus CL of the HS norm of the TLF minus etc., which is bounded by the HS norm of f, which, well, here it's applied with s equals s+1. So eventually what I end up with is this inequality. Now, once I have this inequality, you can write the Lyapunov exponent in the usual way as an average of a logarithm here with respect to the Firstenberg measure. Note that everything depends on E. I get the Lyapunov exponent as the limit of the T sub EL acting on phi sub E. Note that in order to control integrated density of states, it's enough to control L of E. And in order to have uniform bounds for that as a function of E, it's of course enough to get uniform bounds on this creature here. So now you have to think a little bit what it means taking derivatives of this object, but it turns out that basically by the chain rule, these derivatives, say the first derivative for instance, is expressed as such a series. And then when you want to estimate this series, so you want to estimate the derivative, say, in L infinity, this thing is obviously a contraction in L infinity. You have to bound L infinity norms of such, of the derivatives of the derivative of Tm of phi sub E. Now the infinity norm can be estimated, say, by the H1 norm, so you would have to estimate the H2 norm of Tm minus 1 phi E, and then this is why I wrote this inequality down, which is at the bottom here, say the H2 norm. Well, it would be, in that case, would be the H1 norm, would be bounded by E minus CL, would be E minus Cm, an H2 norm. The function f here is just a function capital phi sub E, so that is bounded. And so what you're obtaining here is a convergent series, and you can do similar calculations for higher derivatives. The main point being that you have these very strong smoothing properties of T. How much more time?
Well, I think we got another crowd waiting outside.
Okay.
There,
so let me just say one more minute.
Yeah, sure.
I finish with the following thing here. So local eigenvalue statistics, what you do is that there you're looking at a large box, and then you're taking, so you restrict H to an interval 1n, and so you expect n eigenvalues, and then you take and fix an energy E, take a window, say L over n, a window which is of the order of 1 over n with a large factor. Take the eigenvalues in the window, and you rescale them, and you want to check the statistics. So what Germina and Klopp proved is that this statistics is always Poisson, provided we assume the potential V is sufficiently smooth. And so what goes in that proof are three things. There is Anderson localization, there is a Wegner estimate, and there is also a Minami estimate. So what it turns out is that we are able, in the Anderson-Bernoulli case, to prove this Wegner estimate and this Minami estimate in the situation where we're having, in the situation of the theorem basically, where we're having nice Firstenberg measures and a nice density of states. So of course this requires a different type of arguments. These are not the usual type of proofs say, of a Wegner or a Minami estimate. Essentially, this is a separate statement, is that we managed, it's possible to prove Wegner estimates and Minami type estimates just under the assumption that we have an Firstenberg measures which are, say, absolutely continuous with bounded density, say, and a density of states, say, which is continuous. That turns out to be enough to prove this kind of thing. So this is very different from exploiting one-side distributions, like it's usually, or two sides or so, as it's usually done in these arguments, say, of proving a Minami estimate or so on. So these are different proofs. Now, once you have this statement, of course, you can apply it to the Anderson-Bernoulli model when it's applicable, which means for lambda small and algebraic satisfying these conditions, which in some sense is an extension of this universality principle and a bit against what people believed, is that namely in the random case the statistics should reflect the statistics of the potential, which is very different because the potential only take two values, while we have here an eigenvalue statistics, which is going to be Poissonian, so it's quite a different thing. Okay, so I'll stop here then.
Okay, thank you very much.